object-oriented programming, and solid principles. These two topics come up in every interview and every production codebase. In this video, we'll cover everything. The 4 pillars of aksdev. All 5 solid principles with code. Composition, immutability, exception handling, and the common mistakes developers make. Let's get into it. Quick recap of the 4 pillars. First, encapsulation. You wrap data and methods together inside a class. The outside world only sees what you expose. Second, inheritance. A child class inherits behavior from a parent, code reuse without duplication. Third, polymorphism. One method call, but the actual behavior depends on the object's type. And fourth, abstraction. You expose a clean interface and hide the messy details behind it. These 4 are the foundation. Everything else in this video builds on top of them. Solid is a set of 5 design principles, coined by Robert C. Martin, also known as Uncle Bob. Each letter stands for one principle. And together, they guide you to write code that is easy to maintain, easy to extend, and easy to test. Let's go through each one with real code examples. The single responsibility principle. The idea is simple. A class should have exactly one reason to change. One job. One responsibility. Think of it like a restaurant. The cashier handles payments. The chef cooks food. The waiter serves. If one person did all 3, any change in the menu, or the billing system, or the serving process would affect that one person. Same applies to code. If a class handles database access, email sending, and validation, it has 3 reasons to change. That's a red flag. Here's the problem. This user manager class does 3 things. It saves users to the database. It sends welcome emails. And it validates user data. If the email format changes, you modify this class. If the database changes, you modify this class. If validation rules change, same class again. 3 reasons to change. That violates the single responsibility principle. Now, each class has one job. User repository handles only persistence. Email service handles only emails. And user validator handles only validation. If the database changes, only user repository is affected. The other 2 classes don't even know about it. This is clean separation. Each class has exactly one reason to change. Next up, the open-closed principle. A module should be open for extension, but closed for modification. What does that mean? You should be able to add new behavior without changing existing code. Think of it like a restaurant again. You can add new menu items, but you don't rebuild the kitchen for each one. The kitchen stays the same. New items just follow the same process. In code, we achieve this using polymorphism. Here's the fragile approach. This area calculator uses if-else to check the shape type. Circle. Calculate circle area. Rectangle. Calculate rectangle area. But what happens when you need to add a triangle? You must open this method and add another else if. What about pentagon? Another else if. Every new shape means modifying this existing code. That's fragile. That's the violation. Now, the right way. Define a shape interface with an area method. Each shape, circle, rectangle implements that interface. The area calculator just calls shape.area on whatever it receives. Now, want to add triangle? Just create a new class that implements shape. You never touch area calculator. You never touch circle or rectangle. The existing code is closed for modification, but the system is open for extension. That's the open-closed principle in action. The Liskov substitution principle. Named after Barbara Liskov. The idea: if your code expects a parent type, you should be able to pass any child type and everything should still work. No surprises. No crashes. Here's the classic example. If bird has a fly method and penguin extends bird, but penguins can't fly, then passing a penguin where a bird is expected will crash your code. That's a violation. A subclass should extend behavior, never break it. Here's the violation in code. Bird has a fly method. Penguin extends bird, but overrides fly to throw an exception. Now, If any code receives a bird reference and calls fly, it works fine for sparrow, eagle, parrot. But the moment you pass a penguin, runtime crash. The caller didn't expect an exception. The contract was broken. This is exactly what Liskov substitution warns against. Here's the fix. Separate the abilities into different interfaces. Bird is one interface. Flyable is another. Now, Sparrow implements both bird and flyable. But penguin? It only implements bird. No fly method. No broken promises. Code that works with flyable will only receive birds that can actually fly. No surprises. No runtime crashes. This is how you respect the Liskov substitution principle. Interface segregation principle. The idea: don't force a class to implement methods it doesn't need. Imagine a fat interface with print, fax, and scan methods. A simple printer shouldn't be forced to implement fax and scan, it doesn't even have those features. Instead, split the interface into smaller, focused ones. Each class implements only what it actually needs. Small interfaces. Focused contracts. Look at the bad example first. One interface, machine, forces every class to implement print, fax, and scan. But a simple printer doesn't fax or scan. It's forced to provide empty methods or throw exceptions. Now, the good version. 3 small interfaces: printer, fax, scanner. Simple printer only implements printer. If you have a multifunction device, it can implement all 3. Each class depends only on what it actually uses. Clean and focused. The last solid principle: dependency inversion. High-level modules should not depend on low-level modules. Both should depend on abstractions. Think of it like a wall socket. You plug in a lamp. Tomorrow, you can plug in a fan instead. The socket doesn't care what's plugged in, it's an abstraction. But if the lamp was hardwired into the wall, you'd need to tear the wall apart to switch to a fan. In code, depend on interfaces, not concrete classes. This makes testing easy and swapping implementations trivial. In the bad version, order service creates an email sender directly. It's hardwired. Want to switch to SMS notifications for testing? You can't without changing order service. Now, the good version. Order service depends on a notification service interface. The actual implementation, email, SMS, push notification, is injected through the constructor. Want to test? Inject a mock. Want to switch to SMS? Just pass a different implementation. The high-level module, order service, never changes. That's dependency inversion. Now, a golden rule of object-oriented design. Prefer composition over inheritance. Inheritance models an is-a relationship. A car is a vehicle. But composition models a has-a relationship. A car has an engine. Why prefer composition? Because inheritance is rigid. Change the parent class, and every child is affected. That's the fragile base class problem. With composition, you plug in behavior like Lego blocks. Want a different engine? Just swap it. No changes to the car class. Much more flexible. With inheritance, car extends vehicle and gets everything. Even methods it doesn't need. Tight coupling. Now with composition, car holds an engine reference. When you call car.start, it delegates to engine.start. Clean and simple. And the best part. You can swap engine implementations easily. Electric engine today, V8 engine tomorrow. No changes to the car class. The plugin architecture. This is why the Gang of 4 Design Patterns book says, favor composition over inheritance. Immutability. An immutable object, once created, can never be changed. No setters. No modifications. Why does this matter? First, thread safety. Immutable objects can be shared across threads without any locks or synchronization. Second, easier debugging. If an object can't change, you always know its state. No surprises. Third, no accidental side effects. You pass an immutable object to a method, and you know it won't be modified behind your back. Java strings are already immutable. The same principle applies to your own classes. Here's how you build an immutable class. Step 1. Make the class final, so nobody can extend and break it. Step 2. All fields are private and final. Step 3. No setters. Ever. Step 4. And this is the tricky one, defensive copies. Look at the tags field. If we just stored the reference, the caller could modify their original list and our immutable object would change. So we use list.copyof. This creates an unmodifiable copy. Now, this person object, once created, can never change. Safe to share anywhere. When an immutable class has many fields, constructors get messy. That's where the builder pattern comes in. You chain method calls name, age, and finally call build. Each method returns this, so you can chain them. The build method calls the private constructor. The result: clean, readable object creation. And the person object is still fully immutable. In modern Java, you could also use records for simple cases. But for complex objects with many optional fields, the builder pattern is the way to go. Exception handling. Most developers get this wrong. Here are the golden rules. First, never swallow exceptions. An empty catch block is a bug waiting to happen. Always log or rethrow with context. Second, use specific exceptions. Catch IO exception, not just exception. Third, understand checked versus unchecked. Checked exceptions are for situations the caller is expected to handle, like file not found. Unchecked runtime exceptions are for programming errors, like null pointer. Fourth, never use exceptions for flow control. They're expensive, and they make code hard to read. In practice, Rule 1. Don't swallow exceptions. Log the error with context and rethrow. Now the caller knows something went wrong, and you have the details in your logs. Rule 2. Use try with resources. It automatically closes streams, connections, and any closable resource. Even if an exception occurs. No more finally blocks for cleanup. And finally, when rethrowing, wrap the exception with context. Include the order ID, the operation that failed. This makes debugging 10 times easier. The equals and hashcode contract. If you override equals, you must also override hashcode. The rule equal objects must produce the same hashcode. Here's the correct implementation. In equals, first check reference equality with double equals. Then check the type with instance of. Then compare the fields. In hashcode, use objects.hash with the same fields you used in equals. Why does this matter? Because hash maps and hash sets depend on this contract. If two equal objects have different hash codes, your hash map will lose entries. Hard to find bugs. Some quick tips from Effective Java by Joshua Bloch. First, prefer static factory methods. Methods like value of or of are more descriptive than constructors. Second, use enums for fixed constants. Status.new is better than integer 1. Third, prefer interfaces for types. Accept list, not array list. Fourth, use optional as a return type when a method might return nothing. But don't use it for fields or parameters. And fifth, minimize mutability. Every mutable field is a potential source of bugs. Keep things immutable wherever you can. Let's talk about what not to do. The God class, one class that handles users, orders, emails, and the database. Violates SRP badly. Deep method chains user.getAddress, .getEntry, .getName. That's the law of Demeter violation. If any step returns null, you crash. Instead, expose a helper like user.getEntryName. Public mutable fields breaks encapsulation entirely. Anyone can modify your data. Use private final fields with getters. Empty catch blocks the silent killer. Your code fails, and you never know. And finally, don't use inheritance just for code reuse. That's what composition is for. Here's the classic encapsulation mistake. A public mutable field. Anyone who gets a data object can set items to null, or clear the list, or add garbage. Now the correct way. The field is private and final. The constructor makes a defensive copy with list.copyof. And the getter returns the unmodifiable list. Now, nobody can break your object's state. This is proper encapsulation. Protect your invariants. Quick interview checklist. Can you explain each solid principle with a one-line definition and a code example? Can you show when composition is better than inheritance? Can you write an immutable class from scratch with defensive copies? Can you override equals and hash code and explain why both are needed? Do you know the difference between checked and unchecked exceptions? And can you mention a few effective Java tips, static factories, enums, optional? If you can do all of these, you are in great shape for any OOP interview. And that's it. OOP and solid principles fully covered. If this video helped you understand even one principle better, hit that like button. Subscribe for more deep dive tech videos. And drop a comment, which principle do you find hardest to follow in real projects? I'd love to know. See you in the next one.